Welcome back, it's Ms. Maneely, and I'm going to give you a brief tutorial on how to conduct a test of significance when you want to compare two different population proportions. And so we're going to be looking at the sampling distributions for this kind of scenario. We're going to be looking at tests of significance, and then I'll also give you a quick review of how to complete a confidence interval if you want to compare two different population proportions. This is a little bit different than what we did in the earlier chapters, because now we're looking at two different groups and we're trying to see if there's a difference in the proportion of successes. So we're going to need to understand the sampling distribution for this new random variable. We're going to have to talk about the conditions for inference before we can perform a test of significance. So I tried to abbreviate the notes a little bit so you wouldn't have so much to write, and that we could sort of go through an example as we go through the chapter or go through the section. We're really using the same techniques that we've used all along, so we just have to tweak them a little bit because now we're looking at two different groups. So suppose we want to compare the proportion of individuals with a certain characteristic in population 1 and population 2. So we'll call these parameters of interest P sub 1 and P sub 2. If you were doing an experiment, for example, you might have a treatment group and a control group. So we might use the subscripts T for treatment and control, or C for control. If you're looking at comparing men and women, you can use subscripts M and W. You can use whatever subscripts you want. You just need to make sure that you define them carefully in your problem so that it's clear to the audience which is which. In any case, the ideal strategy is to take a separate random sample from each population and then compare the sample proportions with that characteristic. And ultimately, if we're trying to see if there's a difference or find evidence of a difference, we're going to be performing a test of significance. For example, if we wanted to compare the effectiveness of treatment 1 and treatment 2 in a completely randomized experiment, we'd be looking at the parameters P1 and P2 and then wanting to compare to see if the outcomes are different. And we want to know if that's based on just natural variation, or if the likelihood of seeing the difference that we saw is so unusual that it leads us to conclude that there is a difference between the two groups. So the only thing that starts to get a little tricky now is all of the notation. We're kind of doubling all of the values that we've been talking about. So we have a parameter of interest P, we have our statistic, our P hat, and then we have a sample size. But because we're talking about two different groups, we need to make sure that we're using subscripts to differentiate between the two. So it kind of doubles the number of P's and N's and P hats that we have. So just be really careful. So an observed difference between two sample proportions can reflect a difference in the populations, or it could just be due to chance variation in random sampling. Significance tests, obviously, like we've been doing, help us decide if the effect that we see in our samples is really there in the population, or if it's just, chance. So let's take a look at this example. It says high levels of cholesterol in the blood are associated with higher risks of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? Well, there was a study that was done in the 80s. It says the Helsinki heart study looked at this question, and middle-aged men were assigned at random to one of two treatments. 2,051 men took the drug called gemfibrozil to reduce their cholesterol levels, and a control group of 2,030 men took a placebo. Those are huge groups. During the next 5 years, 56 men in the gemfibrozil group and 84 men in the placebo group had heart attacks. We hope to show that gemfibrozil reduces heart attacks. So just based on that, I'm going to go ahead and use the subscripts T and C to represent treatment and control. So if I were stating my hypotheses, I might say that the proportion of heart attacks in my treatment group is no different than the proportion of heart attacks in my control group. So my null hypothesis is usually that there is no difference in the claim. So I would say something like the proportion of heart attacks in my treatment group is the same as the proportion of heart attacks in my control group. And my alternative hypothesis, I'm suspecting that hopefully this gemfibrozil, this pill, will reduce the rate of heart attacks. So my hope is to find evidence that the proportion in the treatment group is less than the proportion of heart attacks in my control group. So this is one way to set up your null and alternative hypothesis. The thing is, we want to rewrite this so that I'm dealing with one random variable instead of two. And so what I'm going to actually do is rewrite this as a difference between two proportions. So instead of saying that my proportion of my treatment group is equal to the proportion of my control, I'm going to say the proportion of my treatment minus the proportion of my control is simply equal to 0, stating that there is no difference in those two proportions. The alternative hypothesis then, if I were to subtract the proportion from my control group, I suspect that if there's been a reduction in heart attacks, that the difference is actually going to be negative. And you can completely rewrite this. If you want to start off with the control group minus the treatment group, then your alternative would be a greater than. And it won't matter. Your results will be the same in terms of the end. Like your test statistic might be the opposite sign, and your difference in proportions will obviously be a different sign, but your p-value in the end of this test would be the same. The last thing we need to do when we're defining or when we're stating our hypotheses is define the parameter of interest. This time, and like I said, it's important that we think of it as one random variable. My new random variable, though, is going to look like this. P sub t minus P sub c. And I need to make sure that the audience understands what I'm doing. I'm obviously looking at the difference in proportion of men who had heart attacks and I want to make sure that I'm specifying what the T and the C are referring to. And this would be in the treatment minus the control group. The T and the C are kind of obvious, but if you're using subscripts like 1 and 2, you definitely want to make sure that you're labeling which population is your 1 population and which is your 2. So that is what I would need to do for stating my hypothesis. This would be our state step if we're doing a test of significance. Part B, we're actually going to go through this process kind of by hand, talking about the sampling distribution of this new random variable, and then I'll rely on the calculator and we'll do a test of significance using technology in just a minute. The next thing we want to do is look at the sample proportions for each group and then determine the difference in those sample proportions. So one of the things that I think is helpful, because there's so much information, is to kind of create a table. So I'm going to create a little table where I've got my treatment here and I've got my control here. And then I just want to outline the information that I have. So the first thing I'm going to list is my N, my sample size. And so for my treatment group, I can see that there were 2,051 men in that group, and there were 2,030 men in the control group. I also want to take a look at my number of successes. So that's going to be the X, the number of successes in each of these groups. And I can see that 56 men in the treatment group had a heart attack, and I don't know why it's considered a success, even though it's a bad thing, but it's my outcome of interest. And then in the in the control group, we had 84 men. And then I want to figure out my p-hats, my p-hat values. So I'm going to actually leave them as a fraction. So this is going to be 56 out of 2051, and this is going to be 84 out of 2030. Because if my goal is to find the difference, so p hat sub t minus p hat sub c, I simply want to subtract those two quantities. And if I were to come up with the proportions first and then subtract the proportions, I'm going to run into rounding issues. So I'd rather just type them in. So I'm going to go ahead and do my 56 divided by 2051. Whoops. And I'm going to subtract my 84 out of 2030. And I get a difference of, and notice that it's negative, and that's because there were more heart attacks in the control group. So when I subtract, I'm going to get a negative number. And that does sort of coincide with our suspicion that the treatment group is less. So I end up with a test or a sample statistic. The difference is negative 0.014. And that's going to be really important because ultimately what I'm trying to do is determine the probability of getting this difference, and so, or less, if there really is no difference between the groups. If the null hypothesis is true, what are the chances that I'm going to see this difference? Is it really a significant result? So ultimately, I need to calculate this probability. Well, in order to calculate the probability, I need to know the probability distribution for my new random variable, this p of t minus p of c. And what I want to do, because I'm going to be coming back to this difference, this negative 0.014, I'm actually going to store this in a variable. So I'm going to store this in alpha a, so I can come back to it and not have to worry about a rounding error. So I'm going to call this a. And that's just for my own notes. Okay, so let's talk about the sampling distribution of p hat 1 minus p hat 2. If you remember, the sampling distribution for p hat in general, we said was normal, the mean was p, and the standard deviation is p times 1 minus p over n. That was for a single proportion. And we knew that the distribution was normal as long as my successes and failures were more than 10, and as long as the population was at least 10 times my sample size. We're really doing the same thing here, except now we're looking at two different random variables, so we have to remember our rules for adding or subtracting random variables that we learned back in Chapter 6. I think we did this right before the winter break. So if I want to find the new mean, so if I want to find the mean of p hat 1 minus p hat 2, I'm simply going to be, so I basically have two different distributions now. So that's one of them, and then I have another distribution, p hat 2, which is normal. It doesn't actually even need to be normal. And then I'm going to have a new, sorry, I'm running out of space here. All my subscripts will be 2. So if I want to find the difference between those two random variables, if you remember, whatever I do to the means, or whatever I do to the random variables, I'm going to do to their means. And so the mean of my new distribution is just going to be the difference p1 minus p2. Whatever the two parameters are. In this case, I don't know. But the sampling distribution would simply just be the difference in the means. The standard deviation formula is a little bit more complex because if you remember, when we're subtracting random variables, we have to add their variances. And so in order to calculate the variance, remember, I would simply square these two quantities. And we always add variances. So even though I'm subtracting the random variables, I'm going to add their variances. So essentially, if I square both of these quantities and add them together, I'm going to have this piece here. And then to get back to the standard deviation, I take the square root of the variance. Now, I will tell you, this formula is on your formula sheet. You do not have to remember it. And quite honestly, I don't think you'll ever have to compute it by hand. You might see a multiple choice question where the formula is spelled out, so it's important that you recognize what it is. But when we start getting into the inference procedures and calculating the values, I can't think of a scenario where you would physically have to plug these numbers in. Now, as a lesson, I'm going to go through this process, but it's probably not something that you're going to have to do on an assessment. Definitely not on one of mine. And in order to meet the normal condition, we still need to have the successes and failures, but we need to check them for both populations. So for population 1, I need to make sure that the successes and failures are both greater than 10. And for population 2, I need to make sure the successes and failures are both greater than 10. So that's really nothing new. It's a lot, it's tedious to have to list them all, because now you're listing 4 different n times p's and n times 1 minus p's. But it's not really anything different than what we've already done. So why don't we go ahead and verify that all the inference, all the conditions for inference have been met for our situation. Oh, sorry, this is just an image of our sampling distribution for the difference in the two p hats. So our mean is simply the difference in the two parameters, and our standard deviation is just going to be the square root of the sum of the variances. Okay, so we're asked to state to verify that the conditions for inference have been met for the Helsinki health study. So remember, if I'm dealing with inference, if I'm doing a test of significance, I also have to check that my samples were random. And because this was a controlled experiment, it does say in the beginning of the problem that the middle-aged men were randomly assigned to one of 2 treatments. So it's not really a simple random sample, but I can say random assignment. And that's stated in the problem. So I can go ahead and check that off. I have to assume that the population in both groups would be greater than 10 times n. And if you think about it, if I add it together, there's like 5,000 men, or 4,000, I guess 4,081 men. And if I multiply that by 10, so you can actually, since I'm looking at just healthy men, I guess we should actually do both of them. So let's talk about our population of our treatment group. We're looking at there being at least 10 times 2,051 or 20,000. 510 men, that's true. In population in our control group, again, we can still assume that there's 10 times. And this is more just to get you in the habit of checking both groups. Okay, and again, we know that there are plenty of men in this world. And then the last thing would be to check all of our n times p and n times 1 minus p. Now, what we were able to do before when we had a null hypothesis, if you remember when we were dealing with a single proportion, we had a claim about the population. I had a value for p. If you look back at the problem, all we have is the sample data. We have the sample proportions. There is no claim about the true proportion of men who would have heart attacks taking this drug, or the true proportion of men who would have heart attacks taking the placebo. We don't know what the true proportions are. So if you remember when we were dealing with confidence intervals, when we're checking our n times p, so let's go ahead and just, I'm going to list this as treatment and control, because I have to check the successes and failures in both groups. I don't have a p to use. And so if we don't have a p to use, we have to rely on the value of p hat. And so n times p hat, this is, again, this is the number of successes in my treatment group. And the number of successes in this case would be the number of guys who had a heart attack. So I could go back and calculate p hat and then multiply it by n, or if I look in the problem, it tells me that there were 56. So there were 56 men who had a heart attack in the treatment group. That is clearly greater than 10. And if I think about my number of failures, that's just going to be my sample size. My sample size was, let's see, 2051 minus 56. And that is 1995. And that is also clearly greater than or equal to 10, so that condition is met. I can do the same thing for my control group. In fact, you can do a little table instead of having to write number of successes twice. For my control group, I'm looking at 84 men who had a heart attack. That's clearly greater than 10. And then the number of failures would be 2030 minus 84. And that is 1946. And that, again, that is clearly greater than or equal to 10. So all the conditions are met. The only one that we're going to add now is because I'm dealing with two different groups, I also have to assume independence between the two groups. So this is a new condition that we need anytime we're looking at two different groups. And that essentially means that I didn't have a man that was taking both the placebo and the drug. Okay, and that is a new condition that's needed anytime you're dealing with two populations. Okay, so the standard error. So again, remember we said the standard deviation requires knowledge of the true population proportion, which we're not given in this problem. So as usual, if we don't know the true parameter, then we have to rely on our sample value, and then our formula shifts to become a standard error. Well, when we are doing a hypothesis test, remember how we said that we're assuming, our null hypothesis was saying that we're going to assume that the proportion in my treatment is the same as the proportion in my control, which basically would say, if I'm assuming that the null hypothesis is true, I'm saying that there's no difference between the proportions, and in fact, they're all coming from the same population. And if I think of it this way, whenever I'm doing a hypothesis test, we are actually pooling the proportion. This is only something that we do with proportions. This is not something that's done with means. So when we shift gears and start talking about the difference in two population means, we're not going to be talking about pooling. Pooling is only something that we do with proportions. Okay. And so again, the standard error, it's basically the standard deviation formula, except instead of talking about P, I'm talking about my sample proportions. And again, like I can't think of a time when you'll actually have to plug these numbers in. I can see there might be a multiple choice question where you're given different options and asked, what's the standard error, and all the numbers are filled in and you have to choose it. But I can't see an FRQ where you actually have to produce the standard error. But like I said, in a hypothesis test, when we're assuming that there's no difference between the proportions, then we're assuming that the two groups are really just one and the same. And so instead of looking at it as two different proportions, as two different p-hats, what we'll do is we'll pool all of our sample data. And so we'll look at the total number of successes in both samples and divide that by the total of my samples. And then my standard error formula shifts to become this. And this is not on your paper, so you definitely want to write this. And again, This is not something, your calculator will compute this for you when you're doing a test of significance. It'll actually report the pooled value for you. But I can see this being a multiple choice question where you're given a scenario and then asked, what is the pooled proportion or what is the standard error for the pooled proportion? Okay, so let's put this into practice. Let's make some sense of this and go back to our example. So if I wanted to know the pooled proportion or the pooled sample proportion for the heart attacks in the two groups, basically what I'm going to do is I literally write the word pool as my subscript to be careful. Don't call it P sub P. That's just way too many P's. And I want to remember that I had 56 successes in my first group, and I had 84 successes in my second group. And if I add the two groups together, I had 2,051 plus 2,030. And so that's how I'm going to pool. I'm just going to take the total number of successes and divide that by the total number in both samples. So when I pull these together, I'm going to have 56 plus 84. And I'm going to divide that by 2,051 plus, notice that I'm not adding the two fractions. I'm taking the total successes and dividing by the total in both of my samples. So my pooled proportion is 0.0343. And again, because I'm going to be using this number again and again, I'm going to go ahead and store this, and I'm going to store this into variable B. And that way I don't have to keep typing it in. And this will help me avoid rounding errors. Okay, the next thing it asked me to do is to compute the standard error. And again, the standard error of p hat, if it's pooled, is simply going to be, and think about it, it's going to be p times 1 minus p divided by n. So my p hat that I'm going to be using in this case is going to be the 0.0343 times the proportion of failures, which would be 1 minus that. And instead of just dividing by one sample, I'm going to be multiplying by 1 over the first sample plus 1 over. And again, I don't think I've ever had to do this outside of showing students an example. So when I actually go to compute this, it's going to be the square root. And remember, I called this b, so I'm going to say alpha b times 1 minus alpha b. And then I'm going to have my 1 divided by 2051 plus 1 divided by 2030. And like I said, when we do the test on the calculator will give you all this information. And so we end up with a standard error of 0.0057. Okay, and this is going to help us when we actually compute the probability. So when we're doing a test of significance, remember with a proportion we're using a z, we're using a standard normal distribution. Remember, we've already checked that normal condition was met. And so remember again, our null hypothesis is saying that there's no difference between the two proportions. I'm ultimately going to need to compute a z-test statistic, and I'm going to show you how to do that in just a second. I ended up including this diagram on your paper because it does get to be a little confusing because we're shifting from talking about two different numbers and two different variables to talking about a single test statistic or z-value. So remember, it's easier if you actually write your alternative as a difference between two proportions, and that's just a new random variable. And so then I'm going to standardize it like we've done before. So if I'm doing an upper tail test, I'm still talking about that upper tail. If I'm doing a lower tail test where I expect the difference to be negative, I'm going to do a lower tail test. If I'm just looking to see if there's a difference between the two values, then I'm going to do a two-tailed test, and I've got to include that 2 in front. To calculate the test statistic, we're going to use the same process that we've always done. Our observation minus the mean of the distribution divided by the standard deviation. Now we're going to shift this a little bit because now we're talking about the difference between two proportions. Our observation now is that P1, the P hat 1 minus P hat 2. Now in our example, remember we said the difference in our two sample proportions was negative 0.014. Our mean, remember, we're assuming that there's no difference between the two proportions. So P P sub t minus P sub c would be 0. We're assuming that this is true. So this is my mean. My mean is 0. And then we just calculated the pooled test statistic to be 0.0057. And so if I divide those two numbers, I'm going to get the z test statistic for my test. So let's actually go ahead and do that. So z is simply going to be that negative 0.014 minus the 0. That's what I'm claiming is true about my mean, that there is no difference between these two proportions, divided by 0.0057. And again, this is what I called variable A. This is what I called variable B. So if I do this calculation, I don't actually have to subtract the 0. I'm just going to do A divided by B. And my z-test statistic, oops, I did something wrong here. Let's see, negative 0.014 divided by 0.0057 is negative 2. Yeah, that's what I should get. Did I reassign? Okay, I see what I did wrong. This value right here, I did not call B. If I go back, I'll show you the slide real fast. So that was my pooled proportion. This number is my standard error. I'm actually going to go back and I'm going to call that variable C. So I've already gone back up into my calculator. So this outcome that I have here, I'm going to go ahead and store that in alpha C. And so now it's there. So now, when I go to calculate, when I go to calculate this isn't C. I'm doing alpha A divided by alpha C, and I should get, yes, there we go. So there's my z-test statistic, negative 2.47. And again, you will not be asked to compute this going through the sampling distribution the way I have. We're going to do a test of significance on the calculator in just a second, and it's going to look really familiar like what we've already been doing. But ultimately, if I want to find the p-value of the test, if you remember in the first page, we said we're trying to find the probability that the difference in my sample proportions, the treatment minus the control, is less than that negative 0.014. That's what I'm trying to find the probability of. Well, I've just standardized this difference, and I'm calling it a z. This is the same z in the standard normal distribution that we've been using all year. And so notice that the difference really relates to a z statistic of negative 2.47. So we're saying that our result is more than 2 standard deviations away from the mean. And so if I calculate, now I can go to my distributions, and this is a standard normal distribution, so I can go ahead and just choose my normal CDF. And if I'm trying to find the probability that z is less than negative 2.47, my lower bound is going to be negative 9999999. My upper bound is going to be negative 2.47. And actually, let me just recall my previous answer. And that way I'm going to avoid a rounding error. Okay, and so I get a p-value of 0.007. Oops. Okay, and so that's what we're used to getting from the calculator. So it says, what does this value suggest about the effects of gemfibrozole? Well, obviously, since our p-value, which is 0.007, is less than alpha. Now, we didn't set a significance level ahead of time, so let's just go ahead and use 0.05. Since the value is lower, we can say that the result is significant. Okay, that means that we can reject the null hypothesis. Oops. And this means that we have convincing evidence. And this was an experiment, right? It was a controlled experiment. So now I actually can prove causation. We have convincing evidence that gemfibrozole actually reduces the proportion of heart attacks in healthy men. And I guess we should say who take the drug. And we have just performed the test of significance. Now, I am assuming that you guys would rather use the test option on your calculator. So if you go to your stat menu and over to tests, this is a test, and this time we're dealing with a 2-sample test. We're dealing with proportions. So let's see what this looks like if I were to do this on my calculator. We're looking at number 6, a 2-prop z-test. Now if I go back to, I'm going to have to look at my original problem so I have all the information I need. Okay, and so remember that we're saying our population 1 is our treatment group, and so x1, so let's call this 1, and this will be 2 on the calculator. So x sub 1, that's the number of successes. There were 56 successes in my first group with an n of 2051. And there in my second group, I had 84 successes, and that group had 2030. This was a lower tail test. So I'm saying P1 is less than P2, and I can calculate. And so you'll notice that this screen has a lot of P's on it. So we already showed that the conditions for inference were met. So in terms of the do, all you would say is, we proceed with, now it's going to be a 2-sample z-test for proportions. Okay, and so when we get to the math, we're going to write the probability that p hat, so we're still going to have to do the subtraction. We still need to actually do that calculation, that negative 0.014, because I think you'll see that that difference is not actually reported on the screen, so you actually have to do that. But notice that my z-score is there, so I'm just going to rewrite that as z is less than negative 2.47. And my p-value is 0.007. So basically what took me about 20 minutes to go through, you can do in a few seconds using the commands on your calculator. And that is acceptable. The only reason I went through each of those little pieces with the standard error and the standard deviation is because they can and probably will show up as a multiple choice question on your quarterly assessment or on the AP exam. You do not have to memorize those formulas. But you do need to recognize what they represent and how to use them. Okay, so you have one more problem. Okay, this has to do with the National Sleep Foundation. And what I would like you to do is get as far as you can with this problem before you come into class, next class. So try this on your own using the 2-prop z-test on your calculator. I don't expect you to write the standard deviation or anything like that. I want you to set it up just like we did before in the last chapter with using the calculator, where you're going to state your hypothesis. Your plan, remember, is just checking all the conditions. We just have a new condition with checking for independence. The do is writing out the math, and your conclusion statement is going to be the same as it always has been. You're looking to see if that probability is less than the significance value, and in this last example, it's not stated, so you can just use 5%. Okay, so I hope that this comes together, and like I said, we'll review this in class and do some more problems to make sure it sticks.